Hi, welcome to the public key encryption session. Before starting the technical one, we have one announcement.
Hello, my name is Karsten. I'm one of the two RUM session chairs. And I just want to remind you all to submit your best and greatest RUM session talks. Please do so tomorrow, do so today or tomorrow until 12, so we can have the best and nicest program that we ever had at a RUM session at Eurocrypt. If you want to sing, if you want to dance, if you want to perform a poem, read a poem, or even if you just want to talk about your most recent results and announce them, all of that is fine. The more entertaining, the better. So please submit your talks. Thank you.
Okay, then let's start the session. We have 4 talks here. I'm Masayuki Abe, the session chair here. So the first one is by Andrea, talking about public key encryption from isogenies.
Thank you very much for the introduction. Hi everyone, my name is Andrea Basso. I'm a postdoc at IBM Research Zurich, and today I'm going to talk about some recent work that we call POKE, which stands for point-based key exchange, but it's also because I really like eating poke. And this is a new PKE from higher dimensional representations of isogenies, and we're quite excited about it because it's particularly compact and particularly efficient compared to the existing isogeny-based solutions. I'm aware this is not the isogeny cryptography track, so I thought it might be useful to give some context, some history, and how this fits in. And the history of isogeny-based encryption dates back to the 90s, but those were mostly just theoretical results. And the modern history of isogeny-based encryption starts in 2011 with SIDH, which was the first truly practical, concrete implementation of an isogeny-based encryption protocol. And then, roughly 7 years later, C-side was proposed, which was a different isogeny-based PKE that used this commutative group action framework. And SIDH and C-side are very, very different. They use different security assumptions, but if we squint hard enough and we abstract away all the differences, they share some commonalities. And in particular, we can see that both SIDH and C-side look vaguely something like this. We start from an elliptic curve, a supersingular elliptic curve, then one party computes an isogeny, the other party computes another isogeny, and then somehow both of them can complete this square, obtain something like this, where this curve here then acts as a shared secret. And for this to work, what we really want is that the two horizontal isogenies are parallel, which has this technical definition, but basically it just means that the bottom isogeny is sort of like the same on the top, just translated to the bottom. And similarly, we want that the two vertical isogenies are parallel. So what we get is a commutative diagram where we basically get this kind of square structure, which also implies that the shared secret is actually shared by both parties. And the way that, again, SIDH and C-side achieve this is very different, because they are very different protocols, but this structure is common to both of them. So if we go back to our history, as you probably are aware, 3 years ago, SIDH was completely broken in a fairly dramatic reveal with the introduction of these SIDH attacks that showed that SIDH public key would directly yield the corresponding secret key in polynomial time. And as a byproduct of these attacks, we obtained what we now called an HD, or a higher dimensional representation of isogenies. And it looks something like this. If we are given two curves, E0 and E1, which are the starting curve and the end curve of an isogeny, and we're given 2 points on the starting curve together with the action of the isogeny on these 2 points, and we give this additional information on the degree of this isogeny, then this gives us a full representation of the isogeny, which means that we can evaluate the isogeny, we can basically do everything that we're used to do with an isogeny, just given this information. And it's been compared to polynomial interpolation, because in some sense this is similar with polynomials. If you're given how this polynomial is, the polynomial evaluation has sufficiently many points, you can reconstruct the polynomial, and this is similar. If you're given how this isogeny acts on sufficiently large points, then you're given a full representation of the isogeny. And if we go back to our history, the response to the SIDH attacks has been sort of twofold. On one end, there have been approaches like FESTA and QFESTA that developed PKE by using these new techniques that were introduced. So use these HD representations in a constructive way to obtain something that looks very different from C-side and SIDH, but is somewhat efficient. And it could only be possibly achieved after the SIDH attacks because it inherently relied on these new techniques. The other approach is to develop some countermeasures against these SIDH attacks, and we can see many of the SIDH variants like M-side, MD-side, BIN-side, and so on, that instead just try to modify the SIDH protocol to obtain something that was not vulnerable to the known attacks, but did not really rely on these new techniques. And the advantage of this approach is that it still gives us a square like we've seen before, which gives us certain flexibility, especially for advanced constructions, but it came with a very significant drawback in performance. And these two approaches have mostly been very independent. So our goal with POKI was to try to sort of bridge this gap and try to find something that still gave us the same kind of structure as C-side and SIDH, while also use these new techniques from the SIDH attacks to gain in performance and compactness. And this is not totally new. There has been some work like IceCube and Lissy Gamal that tried this approach, but so far it hasn't been particularly efficient or effective. At the core of POKE, of our proposal, is what we call a public-private HD representation. So we want to some kind of representation that can be split into two parts, a public one and a private one. And the public one should be enough for someone else to compute parallel isogenies, which is exactly what we want if we want to build a square like we've seen. But at the same time, this public information should not reveal the entire isogeny all the way, and this should only be possible if we also have the private component. And given a standard HD representation, we can fairly easily construct this public-private representation by doing some slight modification. So rather than including the points, the image of these points as they are, we scale them by some value alpha. Then we also add alpha to our representation, and we call the first two lines the public part and the bottom two lines the secret part. And what we have is that given just the top two lines, we cannot really reconstruct the entire isogeny like we previously did with a full representation. But if we also have the secret information, it's easy to undo the scaling by alpha and get back a traditional HD representation. And given this then public information, as we'll show in the next slide, we can actually compute parallel isogenies exactly like we want. So this is sort of the setting that we're at. We have some secret isogeny phi, we have some points, the orange and the blue points on the left, and we got their images, the images on the right, where crucially the R and S points are scaled by the same scalar. For some technical reasons, the P and Q points need to be scaled by different scalars, but this doesn't matter too much. What we have is that now anyone can compute an isogeny psi on the left by simply taking a linear combination of the points R and S. And they can also do the same thing on the right side by taking the same linear combination of the RA and SA points. And what they get is that these two isogenies are, again, parallel exactly in the same way that we were parallel in SIDH. And what we get is that now, because these are two parallels, this forms a square which can then be completed. Now, on the bottom left, it's possible to, the person who computed psi, the vertical blue isogeny, they can also reveal the images of psi under this, of P and Q, the orange points under this isogeny psi, and they can do the same thing on the right-hand side with the same scaling. And if they do that, what they get is that the 2 points at the bottom are precisely the image of one of the other under this isogeny psi prime, which means that the original person who knew alpha and beta can sort of undo the scaling and obtain a representation of phi prime. Now, we would like to be done here. We would hope that this is enough, but unfortunately, it's not. Sorry, I forgot to mention that sort of if this is maybe slightly confusing because there are a lot of different details, the main takeaway here is that if we have a public-private HD representation, this allows us to construct a parallel isogenies and a commutative diagram exactly like we had in SIDH and in C-side. And I was mentioning before, we're unfortunately not fully done yet because we have that before this curve down here used to act as a shared secret. But now, because this HD representation requires to include both the starting curve and the end curve in the representation, we have to reveal this in the public, which means this is no longer secret. So to solve this problem, what we do instead is that we have to introduce one more set of extra points, which we call X and Y, and then both parties reveal the scaled images of these points. So this happens both up here and down here. And then because we have this condition in the middle, which means that the two isogenies commute, because we are in this commutative diagram setting, then what we get is that both parties can recompute the same set of points XAB and YAB on this curve. So now the shared secret is no longer an elliptic curve, but it's this set of points on this curve down here. And if we put all of this together, now we have all the main ingredients to see how the Poke PKE look like. We start from an elliptic curve, and we define 3 sets of points, the orange, the blue, and the green ones, and they all have different orders. Then during key generation, we sample an isogeny phi of secret degree. This degree, for technical reasons, has a specific shape. And then the public key consists of this curve up here, together with the scaled image of this isogeny phi. So in other words, if we go back to the public-private representation lingo, what we have is that we get the public component of a public-private representation of phi. Then, to encrypt a message, the sender computes an isogeny psi on the left-hand side and computes an isogeny psi prime on the right-hand side, which are parallel, as we've seen before. And they also reveal the scale action of the orange points and the scaled action of the green points. Similarly, on the right, they also reveal the scaled action of the orange points. And for the green points, they compute these, but these are not revealed because, as we said, these act as the shared secret. And instead, they add an additional component CT, which is derived from the message they want to encrypt, XOR with their key derived from these points XAB and YAB. Now, the receiver, in order to decrypt this ciphertext, which is basically everything you see at the bottom, simply uses the orange points PB, QB, PAB, QAB on both sides to reconstruct the isogeny phi prime, evaluate the green points on the left side to obtain XAB and YAB on the right-hand side, and from there extract the message. So this is sort of this is how the Poke PKE look like. Now, if we talk about security of the protocol, we have to formally rely on a computational Diffie-Hellman type of assumption, where we say that computing the green points and the bottom right curve is hard given everything. But somewhat fundamentally, what we rely on is on this problem that we call the unknown degree isogeny problem, which states that we're given, there is this isogeny phi, and we're given the starting curve E0 together with a set of points P and Q. We're given the end curve E1, and together with the action of the isogeny phi on points P and Q scaled appropriately, and we're asking that to recover the isogeny phi even when the isogeny phi has unknown degree. So once again, if we go back to the public-private representation definition, this problem is basically asking to recover the entire representation given just the public component. And in terms of results, our parameters are basically just a description of the size of the three sets of points, the orange, blue, and green ones, and we set these parameters based on the best known cryptanalysis, which gives us, if we put all together, a prime that is roughly 3.3 lambda bits. So not the smallest prime used in isogeny-based crypto, but still fairly small, fairly compact. And if we do this, then we get that our public key is roughly 324 bytes for security level 1, and similarly the ciphertext is roughly double of that. And this is sort of to be expected because we have that the public key is a single curve plus some points, whereas the ciphertext consists of two curves plus points. But luckily, both of these can be compressed using standard point compression techniques, which gives us something that is much smaller, especially in the ciphertext case, where we have that both public key and ciphertext can be reduced to roughly 270 bytes, still at security level 1. And this means that Poke is competitive and comparable to the most compact isogeny-based PKEs that are known, which in this case would be QFESTA. On the performance side, we do not have a full optimized implementation, but we have an implementation in a high-level language. We have some preliminary results in Rust, and if we combine these together with a count of the operation that we expect that we need to do for all steps, what we obtain is that we expect Poke to be the fastest isogeny-based encryption protocol by quite some margin. And just to give a sort of order of magnitude, what we get from our very preliminary results in Rust is that both encryption and decryption should be in the order of a few milliseconds. So just to wrap up, in this work we introduced Poke, which is a new PKE based on this public-private HD representation, and for whose security we rely on a new assumption, which is this unknown degree isogeny problem and its hardness. It has a very interesting efficiency profile because it's competitively compact and possibly the most efficient and performant isogeny-based encryption protocol. And we do this while still maintaining the commutative diagram structure that we had from C-side and SIDH, which also suggests that Poke may be more amenable to advanced construction. If you have any questions or want to know more details, especially in particular about our analysis of this new assumption, please check out the paper or the source code of the proof of concept. Thank you very much.
Questions? Then I have one. How about the efficiency of key generation at the beginning, and also the complex difficulty of choosing parameters?
It's not too complicated. It's slightly more demanding in terms of timing compared to encryption and decryption, but it's still within the same order of magnitude. So it's still very, very manageable. It just takes a little bit longer.
Other questions?
I could have asked you this any other time, but can you compare the security assumption with FESTA? Like, is there a reduction in any of the two directions?
We don't have any formal assumption, any formal reduction in terms of security assumptions. The closest thing we can get in terms of a comparison would be with MD SIDH, because they both rely on isogenies of unknown degree. But then it's hard to get a formal reduction because on one end, here we use isogeny of arbitrary degree up to some definition of arbitrary, whereas there, like a multiple of the degree is known. So there are some caveats, but I think that would be the closest comparison.
Okay, so let's thank the speaker again. Now we move on to the second speaker, Benoit, who will talk about CCA1 security, the message spaces for CCA1 security and homomorphic encryption.
Thanks for the introduction. So I'm going to tell you about CCA1 security in additively homomorphic encryption and in schemes like BGN that also support one level of multiplication. It's a well-known fact that no homomorphic encryption scheme can achieve CCA2 security because it's inherently malleable, but we can still hope to achieve CCA1 security. For example, the light commercial crypto system is CCA1 under the DDH assumption. It's additively homomorphic if the message is in the exponent. Also, in the context of FHE, Canetti et al. Showed that it's possible to build leveled FHE schemes with CCA1 security, either without having full compactness, or using obfuscation, or under non-falsifiable assumptions. But when we look at all these constructions, they can all be seen as being obtained by somehow downgrading a CCA2 scheme and removing the components that make it non-malleable. Then the schemes that we obtain using this approach are about as expensive as the CCA2 scheme they start from. So a natural question to ask is, can we achieve CCA1 security in a more efficient way with an efficiency closer to that of CPA secure schemes? And in this direction, one positive result is Damgard-Selgamal, which is CCA1 under the knowledge of exponent assumption, even if it's a non-falsifiable assumption. But we also have negative results. Last year in Eurocrypt, Schege showed that you cannot prove the CCA1 security of Payet or Elgamal under any standard assumption, and not even under a wide family of interactive assumptions. Back in 2010, there was another paper by Lipma who showed that you cannot prove the CCA1 microphone. You cannot prove the CCA1 security of Damgard-Selgamal under the DGH assumption if the message is a group element. In the paper, we give new positive results. We showed that there is a method to prove the CCA1 security of several schemes by exploiting the smallness of the message space. For example, we prove the CCA1 security of the additively homomorphic version of Damgard-Selgamal under the DDH assumption. We give a proof in the standard model without the generic group model, without the algebraic group model, and even without knowledge assumptions. We don't introduce additional components like a MAC or a key derivation function or anything like that. Actually, there was already a proof of CCA1 security for Damgard-Selgamal, but it was for a hybrid version of the scheme that was not homomorphic. If we consider the homomorphic version with the message in the exponent, then there has been no proof of CCA1 security under DDH, even though the scheme was invented in 91. So we fill this gap in the paper. As a second contribution, we build a CCA1 version of the Bonnet-Gonissim crypto system that evaluates degree 2 functions when the output is small. In this case, we give a proof under the symmetric external Diffie-Hellman assumption in prime order groups in asymmetric pairings. It can be seen as a CCA1 version of Freeman's BGN from Eurocrypt 10. As a third contribution, we also build a CCA1 version of the DL-Gamal-Paillet crypto system that was proposed by Kamenisch and Schupp in 2003. In this case, we have an exponentially large message space. If we compare it with the original scheme, we just lose lambda bits of plain text. Lambda is a security parameter. The reason is that we need to force the lambda most significant bits to be 0 for the proof to work out. Otherwise, in terms of computation, it's as fast as the original construction. In the paper, we also build a CCA1 version of the Castaños-Laguillaume crypto system, which is based on class groups, and which has a prime order message space. So in the talk, I will first give some background on CCA1 security and the hardness assumptions that we use. Then I will explain the three constructions that I mentioned on the previous slide, and I will explain the intuition of their security proof. I'm pretty sure that everyone in the room knows what CCA1 security is. There is a game between a challenger and an adversary. The challenger generates the public key, which is given to the adversary. Then the adversary makes a number of decryption queries on arbitrary ciphertext. And then in the challenge phase, the adversary chooses two messages, M0, M1, and obtains an encryption of one of them, and it has to guess which one it was. Of course, it's a weaker notion than CCA2 because there is no post-challenge decryption oracle, but still it's a meaningful security notion. For example, it implies that you don't leak the secret key when you answer decryption queries. In constructions based on LWE, for example, this is already non-trivial to achieve. And in the following, we will be interested in homomorphic schemes with CCA1 security based on group assumptions. One of them is the decision Diffie-Hellman assumption in prime order groups, in groups without a bilinear map. We use it in the case of Dangercel-Gamal. It's a very standard assumption. In the case of BGN, we will use the symmetric external Diffie-Hellman assumption in asymmetric pairings. In asymmetric pairings between G1 and G2, the symmetric external Diffie-Hellman assumption is just the hardness of DDH in both G1 and G2. And it implies that there is no isomorphism which is efficiently computable from G1 to G2 or from G2 to G1. By now, it's a very standard assumption. In the construction based on Gamal-Paillet, we use Paillet's composite resolutivisity assumption. It's an assumption that says that given an RSA modulus n, you cannot efficiently distinguish a random invertible element of the n square from a random nth residue in the n square. It's also a standard assumption. And we also use yet another assumption that was introduced by Hofheinz in 2012. It's an assumption that says that given an RSA modulus n, you cannot efficiently compute an element C of the n square, which is the Paillet encryption of something not coprime to n. It's a less standard assumption. For example, there is no known reduction from factoring or from DCR, but there has been no attack against this assumption in a decade. So far, it was not given a name, and we chose to call it a composite non-invertibility assumption. Okay, let me begin with the CCA1 security of Dangercel-Gamal. The public key specifies the length of the messages. So we encrypt T-bit messages where T is logarithmic in lambda, the security parameter. The public key also specifies three group elements, G, G1, and G2. And we have another group element H, which is G1 to the X1 times G2 to the X2, where X1 and X2 are a random exponent included in the secret key. To encrypt a message of T bits, the first thing to do is to put it in the exponent of G. Then you multiply it with H to the R, where R is a random exponent. And the ciphertext also contains G1 to the R and G2 to the R. To decrypt, the receiver computes a double exponentiation using C1 and C2 and the secret key. The result is divided from C0, and then the receiver computes a discrete lock in a small interval to compute this little m in the exponent. And the ciphertext is rejected if there is no T-bit message that satisfies this equality. And actually, we will show that this simple interval check is exactly what gives the CCA1 security. We give a proof under DDH, which is very simple. Actually, it's based on the ideas of Kramer and Schoup back in '98. We have a sequence of games that begins with the real game. Then we move to game 1, where we change the generation of the challenge ciphertext. Now we encrypt using the secret key. We compute C1 and C2 as before, but we compute C0 by applying the decryption algorithm in reverse. It doesn't change the distribution of the challenge ciphertext. Then in game 2, we change the distribution of the challenge ciphertext using the DDH assumption. Then in this case, we replace C1 and C2 by random independent group elements. Under DDH, the adversary will not see the difference. And after this change, if we look at the distribution of the challenge ciphertext, then it looks like this. C1 and C2 are independent group elements, but in C0, the message is blinded by a factor that depends on X2, where X2 is part of the secret key. And the crucial thing is that the public key does not reveal anything about X2. But the decryption oracle could leak some information about X2. And to prevent this, we move to a game where the decryption oracle does not use X2. It only uses a different secret key, SK prime, which is completely determined by the public key. But we cannot do this in one step. We do it in Q steps. Q is the number of decryption queries. So for each index I between 0 and Q, we define a hybrid game, a game 2.I, where the first I decryption queries are answered using SK prime, which is completely determined by the public key. And the last Q minus I decryption queries are answered using the real secret key that depends on X2. And we can prove that for each I, the probability that game 2.I rejects a ciphertext that would not be rejected in the previous game is bounded by the size of the message space divided by the order of the group. And the reason is that this event can only happen in the ice query. And before the ice query, X2 is not used at all. And then, since X2 is random on the adversary's view until this query, its action on a maliciously generated ciphertext makes C0 completely uniform. And then this event happens with probability, negligible probability, if the message space has polynomial size. Then when we reach the final game, X2 is not used at all. It's only used in the challenge phase, and it perfectly hides the message in the exponent. And then the adversary's advantage is 0. This is the idea of the proof for Damgarcel-Gamal. In the case of BGN, we need to switch to asymmetric pairings. So we generate asymmetric pairings in groups G1, G2, and GT. And the idea is to use an instance of Damgarcel-Gamal in each one of the source groups. So we, in the key generation, we choose two vectors A and B uniformly of dimension 3. We put them in the exponent. In the secret key, we choose two vectors X and Y that are. To encrypt a message, we compute one Damgarcel-Gamal ciphertext in each one of the source groups. Using additive notations, it looks like this. So we multiply the message by a unit vector, and we add a random multiple of the vector A, and we do the same thing in the second source group. And to decrypt, we can use the secret vectors X and Y to compute an inner product in the exponent and solve a discrete log in a small interval. Again, we reject the ciphertext if there is no small enough message that satisfies both equalities. To do a multiplication, we can use the pairing to compute a tensor product of two ciphertexts in the same way as in Freeman's BGN. So if we have two ciphertexts C and C prime that both consist of 3 elements in each source groups, we can compute pairings of each G1 component of the first ciphertext with each G2 component of the second ciphertext. This gives us a 3 by 3 matrix, which is the product ciphertext. And to decrypt, this product ciphertext, we multiply it on the left by the vector x, and on the right by the vector y. We obtain one group element in the target group, and then we can solve a discrete log in a small interval. Again, we reject if there is no small enough message that satisfies this equality. In terms of efficiency, we obtain product ciphertexts that are made of 9 elements of the target group, and each multiplication costs 9 pairings. Actually, it's possible to build a CC1 version of BGN using the light Kramer-Shoup cryptosystem instead of Damgard-Selgamal, but then we obtain product ciphertexts that are made of 16 elements of the target group instead of 9, and we need 16 pairings to multiply instead of 9. So we obtain a significant efficiency improvement using Damgard-Selgamal. In the proof of CC1 security, we follow the same blueprint as in the proof of Damgard-Selgamal. We have a first game that is the real game. We move to a game where we generate the challenge ciphertext using the secret key instead of the public key. Then we use the symmetric external Diffie-Hellman assumption to modify the distribution of the challenge ciphertext. Then we consider a sequence of Q hybrid games in order to reach a game where we don't use the real secret key anymore. Instead, we use a different secret key SK prime, which is completely determined by the public key. And finally, when we reach the final game, the real secret key is only used to compute the challenge ciphertext, and it perfectly hides the message in the challenge ciphertext. And then the adversary has no advantage at all. This concludes what I wanted to tell you about BGN. Let me tell you a bit about the CC1 version of Elgamal-Paillet. It's very close to the construction of Kamenisch and Shoup in 2003. The main difference is that we restrict the size of the message space to be an interval between 0 and b, where b is smaller than n by a factor 2 to the lambda. And when we decrypt, we check that the plain text is really in this interval. To encrypt, we compute essentially the same ciphertext, we do exactly the same thing as in the Kamenisch-Shoup construction. We compute an Elgamal encryption in the subgroup of 2n's residue, with the difference that the message is encoded in the exponent of n+1, in the subgroup of order n+1, where the discrete log is easy. And then when we decrypt, we check if the message is really in this interval. So the scheme is just as efficient as the original construction, and the ciphertext is just as short. To prove the security, we need both the composite residuosity assumption and the composite non-invertibility assumption. So in the proof, we have a sequence of games that begins with the real game. Then we move to a game where we encrypt using the secret key. Then we change the distribution of the challenge ciphertext using the composite residuosity assumption. Then we use the composite non-invertibility assumption to reject all decryption queries where C0 is a Paillet encryption of something not coprime to n. And then we consider a subsequence of hybrid games where we want to reach a game where the actual secret key is not used in the decryption oracle, but the decryption oracle uses the secret key, which does not depend on the value of the secret key mod n. And then we can make the mod n to hide the message in the challenge ciphertext. To summarize, we described the method of proving the CCA1 security of several homomorphic schemes by exploiting the smallness of the message space. And it gives, for example, the first proof of CCA1 security for Damgart's additively homomorphic Elgamal under DDH. It also gives a CCA1 version of BGN with only nine elements of the target group in the product ciphertext and only 9 pairings to do a multiplication. And we also obtained the CC1 version of Paillet cryptosystem and the CC1 version of Castagnos. There are 2 open questions left. One of them is to avoid the composite non-invertibility assumption when the message is as long as possible. Actually, there is a way to remove this assumption if we restrict the length of the message to be smaller than the square root of n by a factor 2 to the lambda. But I don't know how to remove it when the message is longer. Another open question is to do the same thing with to increase the size of the message space using in the same way as in the Damgard-Zurich crypto system. And in this case, I don't know how to adapt the proof either. And this is it. And thanks for your attention. I'm happy to answer questions.
Thanks. Questions? So, okay, so ask questions offline now. Thanks, speakers again. Okay, the third talk here is post-quantum public key encryption from assumptions beyond LWE and LPN. Didi will give us a talk.
Okay. Hi, everybody. So I'll talk about our work on post-quantum PK from unstructured, noisy, linear algebraic assumptions beyond LWE and Aleknovich's LPN. And so before going into what our construction is and how we use these new assumptions, let me just start by talking a little bit about noisy linear algebraic assumptions. So these are assumptions that look like this. So A, AS plus E is computationally indistinguishable from A, something uniform at random. And typically, noisy linear assumptions can be divided into two categories. One is unstructured, where the matrix A is sampled uniformly from some underlying group or field, and then you have the structured version where the matrix A is no longer uniform. In this work, we'll pretty much only be talking about the unstructured case, where A and S both are sampled uniformly at random, and this error vector E has some special distribution. And two of the most popular assumptions of this family that we know of are LWE, where the error vector is short, so it's usually discrete Gaussian, and LPN, where the error vector is sparse but large. And I say large here because here, every time I talk about LPN, I'll talking about LPN over large fields. And for some nomenclature, whenever we say something, the vector is p sparse, what I actually mean is that with probability p, the entry is going to be non-zero. And typically, for LPN, whenever we talk about sparsity of the vector, it's parameterized with respect to the secret dimensions, which is n in this case. So the probability p would be roughly n to the minus delta, where delta can be thought about as some constant. Now, from LWE, we of course know how to build PKE. Due to regev, we have other constructions, dual regev, and so on. From LPN, if we work in the regime where the vector is sparse, that is delta is greater than 0.5, we do have constructions. That is Aleknovich's LPN from back in 2003. But if you want to work with even denser vectors where the densities, where delta is less than 0.5, we actually do not know any way to construct PKE. And that is where we hit what is usually known as the Aleknovich's barrier. So I have a tiny star mark over there because there are ways to bypass this barrier if you are willing to give out actually exponentially many samples, or if you're happy with quasi-polysecurity, but that is not typically the parameters that we deal with. So with usual parameters, delta less than 0.5, we don't know how to construct PK from LPN. So now, why am I talking about noisy linear assumptions? Well, LW and LPN have been around for a long time. They're well studied, typically believed to be post-quantum secure. And in fact, in the latest NIST candidates for Chem, most of the candidates are either lattice-based or code-based, right? So LW and LPN have been doing a lot of heavy lifting for us for years. The question is, say we are in a world where both LWE and Aleknovich's LPN are potentially quantum broken. Then what? So this is what motivates us to ask the question, can we build PKE from assumptions that are potentially secure even if both LWE and Aleknovich's LPN are broken? So this brings us to our first assumption, which I think is a fairly natural assumption to propose. It's what we call learning with two errors, where the assumption now looks like AS plus E1 plus E2, where think about E1 as the LWE error, so it is short, and E2 as an LPN error. So it's sparse, but wherever it is not 0, it's going to be uniform random from this field. Right? So intuitively, it looks like we have borrowed the best of both worlds from the two well-known distributions in terms of error. And in fact, we can prove that both these, that LW2E is at least as hard as LW in LPN. And intuitively, we can also say that it's potentially harder, particularly because the error is neither small nor sparse. So it's unclear how you would use an LW breaker or an LPN breaker to attack this problem. And a little bit more about the security of LW2E. In fact, with parameters that we use in our PKE, we are unable to show any reduction to, let's say, an approximate CVP or a BDD oracle. But if we, with some parameters, which we do not use in our PK, so beyond the PK regime, we can show that LW2E reduces to approximate CVP with the following parameters. So it's, you can think about n over m as a constant, so it's roughly order of n to the delta over 2 divided by q to the some constant, right? And what we can conjecture is that in the presence of a CVP oracle, which is much weaker, the conjecture it's unlikely that it will break LW2E. And for context, LWE is square root n CVP broken, right? So here, delta is always less than 1, so LW2E requires a much stronger CVP oracle to break. But again, I would like to reiterate that with the parameters that we use to construct the PKE, this reduction does not work. So we don't know any reduction in this regime. So now, is it useful for PKE, or how do we construct PKE from it? So first, let me just give you a generic template on how we use NLAs for PKE. So typically, the public key is of the form A, comma B, where B is AS plus E, and E is the error distribution that you picked. And now, to encrypt a 0, Alice sends 2 uniform random ciphertexts, and to encrypt 1, Alice sends something of the form R transpose A and R transpose B, where R has the same distribution as the error. Right? And now, how does decryption work? What Bob can do is Bob can just take the first ciphertext CT1, multiply it with the secret, and then subtract it out from the second ciphertext. So in case where x was 0, everything is uniform random, so you expect the output of this operation to also be uniform random. But in case of x being 1, if you do the math, it just turns out to be R transpose E. And now if this was LWE, R transpose E will always be small because R is small, E is small, so the linear combination is also going to be small. So we get, we are able to detect the encryption of 0 versus 1. In case of LPN, if we actually set up the parameters correctly, if we set up delta correctly, it turns out that these two sparse vectors just cancel each other out and become 0. And this is specifically where the Leknovich's barrier comes in, because if delta is less than 0.5, these two don't cancel each other out. So, okay, so the question is, can we just use the same approach for LW2E? So let's see what happens if we do this with LW2E. So if you again look at R transpose E, notice that R transpose is from the error distribution itself. So it's of the form R1 plus R2. And if we open this entire thing up, we get a term of the form R1 plus R1 inner product with E2, which is going to be large because R1 is small, but it's dense, and E2 has large elements, so the linear combination is going to be large. And so decryption doesn't really work. So what is the problem here? The problem here is the symmetry of this construction. And what we claim is there is no reason for the construction to be symmetric. We can make it asymmetric. There's no rule that says it shouldn't be so. So we are like, let's pick a different distribution for R. And the distribution that we pick is what we call small and sparse, by which I mean, so R is going to be a sparse vector, but wherever it is not 0, it's going to be small. So think about some Gaussian, discrete Gaussian, wherever it's not 0. Right? And now, if we do the same decryption process, what happens is, so R transpose E1 is going to be small, of course. And then what we hope for is that the two sparse vectors, that is R and E2, will somehow cancel each other out. And if you open up the math, it turns out if we say, let's say that R is n to the minus gamma sparse and E is n to the minus delta sparse, then for this inner product to become 0, what we essentially want is gamma plus delta to be at least 1. And as long as these parameters are satisfied, we are happy. So the correctness would work as long as we pick parameters that satisfy this constraint, but we are going to crucially pick gamma to be less than 0.5 and delta to be bigger than 0.5. I'll come to why in a bit, but this is actually going to be important for security. So keeping this in mind, this is again just a summary of the construction. So the correctness works, fine, we are happy, but what about security? So security, we'll try to do what we always do, just use some hybrid arguments. So first, take B, replace it with something uniformly at random by appealing to the security of LW2E. So B gets replaced with uniform random. Now we are left with this R transpose term, which we would ideally want to replace with something random as well. And now how do we do this? So if you just closely look at it, it looks like if you just stack A and U on top of each other, R transpose, this just looks like very close to LHL, where it's a compressing operation, so we would hope that we get some sort of a leftover hash lemma over here. But if we do a quick sanity check on whether we can actually apply the leftover hash lemma, it turns out that R just does not have enough entropy. The entropy in R, if we do the math, just turns out to be order of n to the 1 minus gamma, but to apply LHL, we actually need the entropy to be at least n log q because we are compressing to an n length vector. So LHL does not work, and in fact, we tried with a bunch of parameters, and it seems there is just no parameters for which LHL and LW2E would work in this construction. So now what? How do we make this switch? Now the point is, okay, probably we don't get a statistical switch, but what about a computational assumption here? And what should this assumption basically be? So let's just make what we need the assumption itself. So the assumption we'll claim is that A comma R transpose A is computationally indistinguishable from A comma random. So it's a computational version of LHL. That's one way to interpret it. And this also looks very similar to SIS. So we call this the inhomogeneous short and sparse integer solution. So IS is IS. And if we are happy with this assumption, then we get the security proof, it works, and we are done with the construction. Now, I gave you some intuition about why we can hope LW2E to be harder than LPN and LWE, but what about ISSIS? Because if that is not harder than LWE and LPN, then there's no point of what we're doing. So how does this assumption relate to LPN and LWE? So before that, I'm going to introduce this assumption in a different form. So typically, all of these noisy linear assumptions have a dual form. Same with ISSIS, where we can interpret this in its dual form, where it becomes something that has the same structure as LWE, where the matrix the A becomes A perp. So now we have A perp S plus E, where E is now short and sparse. So what is crucial in our case is that M is much larger than N. So this matrix A perp is very square. So think about an LWE, or think about this assumption where the matrix is extremely square. So very less number of samples are given out. And it turns out that this particular assumption can be reduced to LPN. And it reduces to LPN with the exact same parameters for sparsity. And this is exactly why we picked gamma to be less than 0.5, because we want to beat Aleknovich's barrier here, because if we pick gamma to be greater than 0.5, then it would be broken by LPN with sparsity, with the same sparsity. So we would not be going past Aleknovich. And that's why it's crucial that we pick gamma to be less than 0.5, and delta is going to be bigger than 0.5 for the construction. Now, what about relation to lattice problems? Well, the natural question we might want to ask is, can we separate ISSIS from LWE, or let's say some approximate BDD, CVP problems? Well, it turns out the answer is no, because in fact, we don't even know how to generally get these separation results without already proving that P is not equals to NP. So we do not really hope to prove such a separation here. But what can we show is that with the parameters that we have, so this is just an example of some parameters. So M can be thought about some constant times N. So here we just pick 20N. And the sparsity it's an extremely dense vector. So the sparsity the probability of it being non-zero is 1 over N to the 0.1. So with these parameters, standard reductions to lattice problem just do not work. And intuitively, the reason is because, as I said, because we are working in such a square regime with ISSIS, it turns out that with these parameters, we are in a we are in a setting what we call the total SIS regime, where the SIS problem with the same parameters can be expected to have exponentially many solutions. And it turns out that there are way too many short vectors which are not sparse. And any CVP or a BDD oracle is just blind towards sparseness, and we just don't know a good way to exploit the sparsity there. So none of these reductions really work. So just to summarize the main result, so we proposed two assumptions, what we call the learning with two errors and ISSIS. We give some evidence that LW2E and ISSIS are potentially secure even if you have access to, let's say, an LWE and an LPN, which is LPN breaking oracles. And we give you a construction. In our paper, we have a lot of reductions in some parameter regimes that work in some parameter regimes that do not work in the regimes that we have our PKE. We have quite a bit of cryptanalysis in our paper, but I would suggest everybody to read the paper if you want to take a look at it. And with that, I'll just leave with some open problems that we are currently thinking about and we would love for everybody to think about. Of course, the most obvious one is, can you build other things other than just PKE from these assumptions? This is what I feel is a provocative question. Can you do some cryptanalysis? Of course, the fact that we don't have any reduction does not really mean that there will not exist one, but it seems unlikely that the current techniques are going to be useful. So there's a lot of scope for cryptanalysis here. And then finally, what I think is a very interesting problem is, can you just take LW2E, which is a combination of LW and LPN in some sense, and build a PK straight out of it without the use of this helper assumption that we call ISSIS. And yeah, that's it. Thank you. And I'll take questions.
We have some time for questions.
Hi. Thanks very much. A question about the ISSIS.
Yeah.
So it looks like you're using a very sparse and short vector as the input to the SIS function. And it's in a regime where it's an injective function, is that right?
Yes, it's the non-total regime for ISSIS, yes.
So I guess, there's kind of a way of viewing this also as an LWE problem where just the vector is the error vector and you're kind of in a normal form LWE. So I'm wondering how the security of that relates to like ordinary LWE since the error is much sparser and shorter here.
Right, yeah, so we do have a reduction to LWE for ISSIS, but using the noise flooding techniques, but that reduction only works if we have if the sigma or the width of the Gaussian error and the modulus is exponential. Mm-hmm. It does not work with polynomial sized sigma and Q. And when it comes to trying to relate it with let's say an SIS breaker or a CVP breaker, the thing is because it's so square, LWE with the same regime is actually statistically indistinguishable from random. So that's why the reduction to LW doesn't really work directly.
Yeah, I guess my question is maybe more motivated by like just lattice reduction. If you just throw a BKZ solver at this, does it find this very sparse vector or not?
We do have some analysis there as well, where we tried to throw a BKZ or an LLL solver to it, and it still works in exponential time in the number of samples that you have. So 2 to the m order of m. That's typically what we see here.
Thanks.
Other questions?
Hi, I have a question on the ISSIS assumption that you mentioned. So you connect that to the LWE with sparse and small error, right? And the way that I would think of is that, okay, if I can find a ISSIS solution, then of course I can break LWE with the small and sparse error. The issue is that I think your assumption is that the ISSIS assumption you want is sort of a pseudo-random assumption, right? You want to say that the small and sparse vector multiply A is pseudo-random.
Right.
Is there any intuition fitting this gap for it? Like
sorry, maybe I missed the
how do you
question.
get from search hardness of the sparse and small vector R to the pseudo-random argument that you want?
So we do have a reduction from the search between the search and the decision version of this ISSIS.
Oh.
And it's actually sample preserving, so the same dimension, same parameters just.
Okay, I see. So there's a reduction.
Yeah, there is a reduction between search and decision. Yes.
Okay, so let's thank the speaker. So the final talk here is by Fabrizio about Fujisaki Okamoto transformation.
Yes. So thank you for the introduction. And today I'm going to talk about a joint work with Katrin Hovermans, Andreas Husing, and Christian Mainz about the encryption step in the F4. So let's start with why are we interested into this? Of course, most of the proposals to the NIST standardization process make use of the F4, and there is one step in this transformation called re-encryption that on one side solves some problems, for example, ciphertext malleability, but on the other side is weak against side channel attacks. So what we did in the paper was we actually performed a study of already existing solution for, already existing alternative to encryption provided by Entru and McAleese. And we formalized a computational notion that is also provided by re-encryption and show how to use it to attain CCA security at the end of the transformation. And we prove also like a new QROM statement in case of chems with explicit rejection. And at the end, we prove that there are cases in which the curse of the re-encryption is actually unavoidable. So there are cases in which we cannot avoid the side channel weakness. Okay, I'm gonna quickly introduce the F4 transform. I gave some results about it. Then I'm gonna introduce these frameworks that allow us to generalize the type of function that re-encryption represent, and then I'm gonna actually talk about our analysis. So let's start with the F4 transform. It was introduced by Fujisaki Okamoto, no surprise, but the version that we use nowadays is actually due to that. And here, I just wanted to give you like a really rough idea of how to use encryption and decryption to define encapsulation and decapsulation. So, quick disclaimer, throughout the presentation, I'm always gonna use explicit rejection, as you can see in here, in line 8. So if something goes wrong, I'll just send a failure message. In the paper, we also have results for implicit rejection. And then I want to highlight two steps. So in line 2, in case we start with a randomized PKE, we use a random oracle to de-randomize because the transformation needs a deterministic PKE. And then actually in line 6, I highlighted the re-encryption step. So we first decrypt, and then we need to encrypt again to add the check provided in line 7, 8. And this is what was actually exploited in the paper by Wen et al. Called cursor re-encryption, and in particular, the fact that if we have to implement the transformation, we have to implement, we use an hash function to implement the random oracle. And they described a key recovery attack that they apply to most of the actual proposal to the NIST standardization process. And our goal was to kind of study if it's possible to avoid this, this vulnerability. But going back on the FO itself, in a later paper, Hoffins, Hovelman, and Kiltz provided this modular analysis of the transformation where they split the transformation into smaller one to get, let's say, better analysis. First of all, to separate the functionality provided by each transformation, and then to obtain better, to move from one transformation to the others. So they introduce the T-transform that takes as input a PKE and a random oracle and output a deterministic PKE by using the randomization, and it provides it performs the re-encryption step. And then they introduce the U-transform that is actually the one that converts the PKE into the chem. And in a later paper, while studying the case of a deterministic PKE, Bernstein and Persichetti introduced this notion called rigidity, that is actually what is needed to get the CCA security of the U-transform. And we say that a scheme, a deterministic PKE is rigid if for all key pairs and all ciphertexts the following holds, or we get direct failure during decryption, or if we encrypt into a message, then we have to encrypt again into the same ciphertext. So 2 quick observations about this notion. The first one is that it doesn't make sense to define it for randomized PKE, because of course by taking 2 different randomness, the encryption will lead to, most likely, to different ciphertexts. And also, yes, if we only apply de-randomization, the deterministic PKE that we attain will most likely still be non-rigid, because we're adding no checks during decryption. Okay, now that we have all we need, we can actually go into our contribution. And we want to first relax the assumption, the notion of rigidity, by introducing a computational version of it. And we say that a ciphertext is non-rigid if there exists a key pair for which, let's say, the rigidity statement doesn't hold. And then in the paper we define a game that we call find non-rigid ciphertext, where the adversary takes as input a public key, and it has to output a list of ciphertexts, and the adversary wins the game if in the list there is a non-rigid ciphertext. Now, to keep everything simpler, I will just call this notion rigidity throughout the presentation. So if I not call it computational rigidity, I'm still going to refer to this. And okay, now we introduce some bad ciphertext, right? And we would like to understand how can we get such a ciphertext. So let's pick a deterministic PKE, and let's assume that we have a non-rigid ciphertext. By assumption, it means that C and C prime are different. And now we have only 2 possibilities. The first one is that C is the encryption of a message, and since the PKE is deterministic, the message has to trigger a decryption failure. And this is a case that we can bound by known technique. We can use correctness assumption, or in case that the PKE is perfectly correct, this is not even a case. So the second case is the most interesting one for this paper. It is the case in which the ciphertext is the encryption of no message. So once we fix the PK, the public key, and we see the encryption as a function of the message, we cannot reach the ciphertext. In this case, we say that the ciphertext is not in the range of the encryption. So to focus even more on this, we can just assume from now on that all the PKs that we are studying are perfectly correct. So we can just focus on the second case, right? Okay, so now we need something that allows us to answer the question, is this ciphertext the encryption of a message or not, right? And our first answer is, let's say, an abstract one. We can define an oracle that we call range checking oracle that actually answers this question. Then a more concrete answer is the algorithmic version of it. So we call an implementation of such an oracle a range checking algorithm. And we want to keep the definition general so that, like, we can say that, for example, re-encryption is a range checking algorithm, right? And at this range, the re-encryption actually provides both, let's say, a good and a bad implementation. Indeed, in the case of a perfectly correct PKE, the re-encryption is actually a perfect implementation. It means that every time we give a ciphertext as input to the oracle and to the algorithm, they will give the same answer back. In case instead the PKE is not perfectly correct, there are ciphertexts on which the oracle and the algorithm disagree on. So what we did, we also formalized a notion, a computational notion that allows to estimate how good the implementation is, so how good the algorithm approximates the oracle. And again, to keep things simple, I will just, if I need a range checking algorithm to fulfill this notion, I will just say that the algorithm is a good approximation or a good implementation of the oracle. Okay, now before going into analysis, I said that we were like generalizing re-encryption, but the only example I gave you so far is re-encryption again. So let's see actually some alternatives. And these alternatives are provided by McAleese and Entrue. So these are just like a really high-level version of the possible checking algorithm that we can implement. But in McAleese, so code-based PKE, what we do is that we decrypt, and through decryption we get like an intermediate value that has this really nice property. It has a specific weight if and only if the initial ciphertext was. And this means that we have an equivalent condition of being in range. And this actually provides a perfect implementation of the range checking oracle for the McAleese scheme. Then in the case of Entrue, instead, both ciphertext and messages are polynomial, and the coefficients of this polynomial belongs to really small sets. And here instead what we do, we check the coefficients of the ciphertext. If they belong to the proper set, we move on, we actually decrypt, and we do a similar check with the message that we got during decryption. And also in this case, we get a perfect implementation. Okay. Now we can actually move to our analysis. So in the previous module analysis that I introduced, the FO transform was split into the T and the U transform. What we did in the paper was actually to, let's say, to split it even further, even if it's not exactly correct. What we keep the same U transform as the previous module analysis, but instead of the T transform, here we have other two transformation. The DARE transformation is the one that actually provides only de-randomization. And the core of the analysis is actually the RIG transformation. That is the one that provides rigidity by using this range checking notion that I introduced before. So again, disclaimer, this is like a simplification of the result that we have in the paper. In the paper, we also have, as I said before, results for the implicit rejection case, and you can find the full figure in the paper. And now let's move to the actual analysis, and we start with the core. So here, we can define the RIG transformation as the one that takes as input a deterministic PKE and a range checking oracle that I call range here. And the main modification that it applies to the PKE is here in line 5, that we had the check given by the range checking algorithm. And what we actually prove is that the intuition that I gave you before with the clause was actually correct. Indeed, by using some correctness assumption of the PKE and some assumption on the range checking algorithm, the transformation actually provide rigidity. And that's what we needed to move on to the next step, to the U transform. And since we did the checks before, during the previous transformation, here the U transform only has to convert the PKE into the chem. So it means that we only need to use the encryption to define encapsulation and decryption to define decapsulation. And what we actually prove is security reduction both in the ROM and in the QROM for implicit and explicit rejection. In particular, in the QROM and in the case of explicit rejection, we prove a new statement that actually has like a simpler assumption here that than previous result. They had like some assumptions that are kind of hard to check, let's say. And then, now going all back to the beginning of the transformation, what we actually, this transformation is just the de-randomization step. So we use a random oracle to de-randomize in case we had a randomized PKE, right? And now what we actually get is that in case we have to de-randomize, for the de-randomized PKE, the only good range checking algorithms that we can define, these are actually, they have the same type of weakness that re-encryption has. And this means that at some point of this algorithm, we have to query the random oracle to make the range checking algorithm good. And this means that like a similar attack as the one described in cursive re-encryption could still be feasible and could still threat the side channel security of the implementation. And So just to summarize, what we did, we formalized the notion of computational rigidity, and then we analyzed alternative to re-encryption as the one provided by Entrue and McAleese. Then we introduced this framework with the range checking oracle and range checking algorithm, and show how to use it both in the ROM and in the QROM to obtain CCA security at the end of the FO transform. And then we proved that like there are some cases in which the curse is unbreakable. So that's it. Thank you.
Thanks. Some questions?
Hi, thanks for the excellent talk. I was wondering about the final takeaway message of the course. Do you think there is any alternative technique to the randomizing that won't require you going through a random oracle?
Yeah, so like the thing is that like if we want to kind of avoid like this type of attack, or we have to do something completely different, or it turns out that like countermeasure against a channel attack has to be used anyway. Like you cannot only rely on the transformation in that case, right? Because
Now, you don't think there could be any hardness assumption where you don't need necessarily like true randomness during encryption, and then maybe it's, I don't know.
Say it again, sorry?
I don't like the cars. I don't like the cars. It's just, yeah, if there was any way of not going through a random function, but still having some sort of re-randomization, so that then maybe you can reconstruct things in a cheaper or in an implicit.
There are like in the paper we also analyzed some alternatives that we find like in the literature, some of which are not that great, but a possible way of doing it could be by defining some function that allows you for randomness recovery. So in that case, to recover the randomness, you don't have to call the random oracle, and maybe you can rely on that. But we didn't went through the details in this paper.
Thank you.
Thank you.
Other questions? Okay, then let's thank the speaker again, and let's thank all the speakers in this session.